So this lecture is going to be a bit more mathematical. We're going to talk about heat capacity. So the transfer of thermal energy from one body to another causes either a temperature change or a change of state or both. However, different substances require different amounts of energy to increase the temperature of a given mass of the substance. This occurs because different substances have different capacities to hold thermal energy. This is known as the specific heat capacity of a material. For example, water holds thermal energy better than steel, so water is said to have a higher specific heat capacity than steel. This table gives you some specific heat capacities of different materials. You see water is the highest on the list at 4.18 times 10 to the power of 3. Specific heat capacity doesn't have a unit particularly. It's joules per kilogram degrees Celsius. 1 joule is the amount of energy needed to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. That's another way we can read a joule. That's an interesting thing to know because it relates directly to the ability of something to be heated. So here's specific heat capacity. This is given the symbol of C, lowercase c. It's the amount of energy required to increase a substance of 1 kilogram by 1 degree Celsius. It's measured in joules per kilogram degrees Celsius. It also would be the amount of energy released when a substance cools down by 1 degree Celsius. So you might want to write the note as well. So the total amount of thermal energy transferred from a warmer substance to a colder substance is called the quantity of heat. It's given the variable Q. And it's calculated using this equation. Q equals mc delta T, where C is the specific heat capacity, m is the mass, and delta T is the change in temperature. So if an object absorbs energy, then its final temperature is greater than its initial temperature. That means the value of delta T is positive and the value of Q is positive. But if an object loses energy, the final temperature is lower than the initial temperature. That means the value of delta T is negative and Q is negative. So copy this down. This is an important equation to know. Q equals mc delta T. I've already mentioned what they are, but just be aware that C is the specific heat capacity and Q is the energy lost. Specifically, it's the thermal energy lost or gained. Lost when it's negative, gained when it's positive. So here's our first question. It says, if the specific heat capacity of water is 4,180, how much thermal energy is needed to raise the temperature of 2.2 kilograms of water from 20 degrees Celsius to the boiling point, which is 100 degrees Celsius? So we have Q equals mc delta T. And we need to substitute what we know here. M is 2.2. C is 4180. Delta T is going to be the difference between 100 and 20. So let's work this out and calculate it. 100 minus 20 is 80, so I'll just write down 80 times 4180 times 2.2. We get 735,680. So 735680. And then I have to round for significant digits. And I'll write it in scientific notation as well. That is our energy. If it doesn't state that you have to write it in any other type of, if we don't have to write this in kilojoules or megajoules, so we can just write it in joules with significant digits. Okay, next. Oh, I should turn this camera off. copper pot is sitting on a burner. The pot has a mass of 1.2 kilograms, and the temperature of it is 130 degrees Celsius. The pot cools to room temperature of 21 degrees Celsius. So while it was cooling, it lost energy to the environment. So let's find out how much energy it lost. By doing that, we would use our Q calculation. So let's turn this on again. So in this case, it's Q equals MC delta T. But our M is 1.20. Our C is 380. And our delta T is 21, which is the final temperature, minus 130, which is the initial. So let's turn our calculator on. 21 minus 130 is negative 109 times 380 times 1.2. We have negative 49704, and that is going to round to 5.0. Let's see here. How many significant digits do we have? I'd argue we only have 2, because 3.80 isn't clear if it has 2 or 3 significant digits. So I would write this as negative 5.0 times 10 to the power of 4 joules. Because when I look at the question, I see 3 significant digits for the mass, the temperature of the air in both situations, but the 380 isn't clear if it's in if it's 2 significant digits or not. I'd like you to copy down this principle of thermal energy exchange. It says when thermal energy is transferred from one object to another, it normally flows from the warmer object to the colder one. The amount of the thermal energy transferred obeys the principle of thermal energy exchange, and that is stated here. When thermal energy is transferred from a warmer object to a colder object, the amount of thermal energy lost by the warmer object is equal to the amount of thermal energy gained by the colder object. So what does that mean? If we're trying to cool down pop in a can, you would put it in ice. It's not the cold that's transferring to the ice. It's the thermal energy of the can that's transferring to the ice. So you actually are heating the ice. And by heating the ice, the can is losing energy. So it's becoming colder. That's the concept of thermal energy exchange. So considering the law of conservation of energy, this makes sense. Because of conservation of energy, we will never have a loss of energy. So our Q lost plus our Q gained has to equal 0. Notice that the Q lost is negative and Q gained is positive. So they would, when we add them together, they would be the same magnitude, but one would be negative, one would be positive. So here's the principle of thermal energy exchange as an equation. Now let's do some problems that involve using different substances which have different specific heat capacities. So in this question, it says here that we have a 60 gram sample of a metal, and it's heated to 100 degrees Celsius. And then it's placed in 200 grams of water with an initial temperature of 10 degrees Celsius. The metal-water combination reaches a final temperature of 15.6 degrees Celsius. So we have to identify the metal, and we can do this by determining its specific heat capacity. So let's start. We'll start with what is the energy lost and the energy gained. So let's first find our Q lost plus Q gained equals 0. And this Q is, the Q lost is MC delta T. Well, we got to put the subscripts in. So the 60 gram metal goes from 10, it goes from 100 Celsius, and then we have water at 10 Celsius. So it is going to lose energy. So MC delta T of the metal, the water is going to gain. So this is the M, I'm going to call this subscript M, plus the water, which gains everything. So Q, I'm going to rewrite it as M subscript W, C subscript W, delta T subscript W. So what I've done here is I'm labeling that my metal is the one that's losing, my water is the one that's gaining. So we know they're going to have a final temperature of 15.6, but let's figure out how this works out here. So my metal is 0.60 grams. The C for metal, we don't know. We have to solve for that. Sorry, I should do that first. I have to rearrange this to solve for Cm. So that would move to the other side of the equation, become negative. I would divide by the delta Tm and the mm. So my Cm equals negative mass of the water times specific heat capacity of the water times the change in the water's temperature divided by the mass of the metal divided by the temperature change of the metal. That's my full equation. So mass of the water is 200 grams. 200 grams, like that. The C of the water is 4180. And the temperature change of the water is 15.6 minus 10. Divided by the mass of the metal, which is 0.060. And the temperature change of the metal, which is 15.6 minus 100. So let's do all of this in our calculator. And we'll start with, it's going to be negative, so 0.2 negative times 4180 times bracket 15.6 minus 10. Close the bracket. That whole thing divided by bracket 0.060 times bracket 15.6 minus 100. Close the bracket, and it equals, we get 9 to 4.5. Rounding it, we get 920 joules per kilogram degrees Celsius. And now we have to see, I'm going to move the calculator out of the way and the paper out of the way, because we need to see what type of metal this is. So 924, it's closest to aluminum. So we can then say, because aluminum is 9.2 times 10 to the 2, which is 920. Therefore, the metal is aluminum. And that is our answer. Okay, now another question. 200 gram piece of iron at 350 degrees Celsius is submerged in 300 grams of water at 10 degrees Celsius to be cooled quickly. Determine the final temperature of the iron-water combination. Okay, this is going to be involve some other algebra to do, so we're going to I'll do this one with you. It's pretty interesting because we have to combine our two TFs together. So we have Q lost plus Q gained equals 0. First thing we need to do, one of these things is going to lose energy, one is going to gain energy. So I'm looking at this and I see the iron losing energy and the water gaining energy. And that is because the iron is cooling down. So I'm going to put M of iron, Fe, C of Fe, delta T of Fe, plus MW, CW, delta TW equals 0. So we can read this from the table to figure out what that is. But before we do, let's change these into their initials and their finals. So MFE, CFE. My final energy is what I need to find. So TF, it's combined for both of them. But my initial, I'm just going to call it TFE because my initial iron energy is, I don't need to put the I in there because I've already can see that it's the only thing that would have a subscript FE. And then here we have my TF minus TW. So I need to isolate this for TF. So to do that, what I'll first do is I'll expand everything. And I'll write the TF in front. TF, MFE, CFE minus TFE, MFE, CFE plus TF, MW, CW minus TW, MW, CW equals 0. Now I have to factor this out, and I'll move these two to the other side of the equation. TF is MFE, CFE minus MFE, minus this here. So that is MW, CW. So this is the TF I'm factoring out. And it's actually plus, not minus. This term plus that term. And then here, these two minuses are going to move to the other side. They're going to become positives. And we end up with T FE, MFE, CFE plus TW, MW, CW. And then lastly, my TF is everything here divided by that sum there. So T, FE, M, FE, CFE plus TW, MW, CW divided by MFE, CFE plus MW, CW. So all of that, I am now going to substitute my values in. So my iron temperature is 350. My mass of my iron is 200 grams, so 0.2. My C for my iron, reading from the table, it's 450. And I'll just quickly turn this off to show you. It's right here. 450. 4.5 times 10 to the power 2. The T for my water, the initial temperature of the water is 10. The mass of the water is 0.3, 300 grams. The C of the water is 4,180. Divided by the mass of my iron, which is again 0.2. The C of my iron, which is 450. Plus the mass of my water, 0.3, plus the C of my water, the specific heat capacity. So this equation here is then put through my calculator, and I'll move it to the side so I can turn my calculator on and see it at the same time. So my numerator, bracket, 350 times 0.2. Sorry, I screwed it up. I'm going to redo that. So bracket 350 times 0.2 times 450 plus 10 times 0.3. The calculator's buttons are too close to each other on here, so let me try this again. 350 times 0.2 times 450 plus 10 times 0.3 times 4,180. Close the bracket. That's my numerator. Divided by the denominator. 0.2 times 450 plus 0.3 times 4,180. Close the bracket. Equals 32.7. So TF is 32.77 or 33, because we have two significant digits as our minimum, degrees Celsius. That is our solution to that problem. So quite a bit of algebra there to find the TF and isolate it, but that's how you would solve that. We haven't talked officially about thermal expansion yet, but as things get warmer, their particles move faster, and that tends to cause solid objects to sort of spread out. We don't really see this a lot in like larger materials like metals and things, but if you had a concrete on the road, for example, and it was all one big slab, you'd eventually get cracks appearing. That's why the concrete slabs are sort of designed in smaller amounts with little gaps between them so that they can expand. You might have noticed or driving over some bridges that they have these metal grates right here, and those are designed so that the metal in the bridge has a space for it to expand. Contraction also occurs, though. When things get colder, they tend to get smaller. So that's something else to consider as well. Note here says all substances that expand in warm weather also contract in colder weather. So write this down about thermal expansion and contraction.